All right, good morning, everyone, and hello, and welcome to the Physiology of the Heart lecture. The physiology of the heart is very, very complicated, so we are going to simplify and talk about the conducting system of the heart. So, the conducting system of the heart is what gives us those beautiful beeping sounds and when somebody is hooked up to an EKG machine and it has our we can see our conducting system working on an EKG, which is the electrocardiogram that doctors can hook you up to if they're worried about your heart. All right, so we're going to look at that in just a few minutes. But I want to start by going over the fact that there's going to be 5 different steps to your heart contracting. And I also want you to understand that your heart has to deal with physics, right? The fact that fluid, when it moves, it takes time. When electricity moves, it takes time. And your heart accommodates for all of those fascinating things. Okay, if you're interested and you need more help, this information is found on page 400 in your textbook. So if you need to use your textbook, I do advise it. It's a great resource for you. All right, so don't forget that. Okay, so again, we are going to start with 5 different steps that will allow us to follow the flow of electricity through the heart. So notice the 1, 2, 3, 4, 5. The 4 and 5, don't get them confused. Notice 1 goes to 2, 2 goes to 3, and 3 travels down that interventricular septum. Okay, and that is what makes 4, is what's in the interventricular septum, and then 5 is what's going up on the outside of the heart wall, so up the walls of the ventricles. Okay, so hopefully you'll understand now why it is so important that we understand the parts, because when I start talking about 1 is the sinoatrial node. Sino meaning the sinus, atrial meaning the atria, and node meaning a place where the impulse is coming from. All right, so very interesting. The original activity is going to start in that SA node. Okay, so the SA node is going to send a signal, again, it's an electrical signal, through the wall of the atria. And that is step 2. That stimulation, again, we're talking action potentials. So don't forget that you're going to have a depolarization, a repolarization, all of the same things that you learned in the nervous system about the movement of electrical charges throughout the body, travel in action potentials. Okay, so these things are building, one concept building on another. All right, so the stimulus then is going to spread through the neurons that are in the wall of the atria. Okay, these are specialized cells, and you can see in the diagram they wrap around kind of the outside of the atria there, and then they're going to take it to the atrioventricular node. So notice that we have different names, but the names tell us where they are. The sinoatrial node is in the sinus of the atria, meaning the space of the atria, very close to the superior vena cava. All right, and then the message is passed to the atrioventricular node. And just like we talked about the AV valves, they're in between the atria and the ventricle. We now have the AV node, which is in between the atria and the ventricle. Okay, so from there, it's going to travel down the AV bundle, as it's called. So notice in between the atrioventricular node and the bundle branches, you have the AV bundle, the atrioventricular bundle. Okay, and interestingly enough, we have an elapse of 50 milliseconds here. And this elapse of time right here is going to allow for the blood to move from the atria to the ventricle. So, you think about how long it takes for you to fill up a glass of water, how long it takes for you to fill up a bucket of water, right? So if it is a small amount of fluid, it takes a small amount of time for that fluid to move. If it's a large amount of fluid, it takes a large amount of time. So the heart actually is accommodating for this. If the heart's squeezing when the blood's moving, that blood's not going to move. So the blood has to have that space in the ventricle, and this elapsed time here in step 2 is going to allow that blood to move in between these two things, okay? I just was stuck on the 50 milliseconds. I'm so sorry. There's a 100 millisecond delay at the beginning of the AV node contraction because of what I was just saying. This time elapsed here. This is the whole thing from start time 0 being in step 1. And so then 50 milliseconds later, that action potential is traveling around the atrium. When we get to step 3, we are only at 150 milliseconds. As we move down to step 4 is now transferring from the AV bundle to the bundle branches. And in the bundle branches, you're going to notice now that we have a split between left and right. And the split between left and right is going to be important so that way we have a consistent and concise contraction of both ventricles at the same time to have the best output, okay? So when we get to step 4, it is traveling along that interventricular septum and it is branching into what we call the Purkinje fibers. And the Purkinje fibers are going to be the ones that wrap up the wall of the ventricle. And they kind of reach out in all directions, making sure that, again, there is a consistent and concerted effort for the heart to squeeze all at once, okay? And once this is done, well, that's a heart contraction, okay? And it starts all over again. Let's take a look at this.
Action potentials originate in the sinoatrial node and travel across the wall of the atrium from the sinoatrial node to the atrioventricular node. Action potentials pass slowly through the atrioventricular node to give the atria time to contract. They then pass rapidly along the atrioventricular bundle, which extends from the atrioventricular node through the fibrous skeleton into the interventricular septum. The atrioventricular bundle divides into right and left bundle branches, and action potentials descend rapidly to the apex of each ventricle along the bundle branches. Action potentials are carried by the Purkinje fibers from the bundle branches to the ventricular walls. The rapid conduction from the atrioventricular bundle to the ends of the Purkinje fibers allows the ventricular muscle cells to contract in unison, providing a strong contraction.
Awesome. Okay, so with access to the notes, you can go back and watch that again if you want. But simply that is how this works. There's another video here that is going to do the same. So it again is in the notes. I think the more times we see this and the more times we pay attention to it, the better. If I put this on full screen, it becomes very blurry. So just enjoy it small.
The heart is a beating muscle that continually pumps blood to the rest of the body. What we commonly call a heartbeat is actually the rhythmic contraction of the heart's 4 chambers. Each heartbeat is stimulated by electrical signals that travel through a specific nerve pathway in the heart. These signals can be tracked and recorded by an electrocardiogram, or EKG. The heart's electrical signal begins at the sinoatrial node, or SA node, which is located in the top right chamber, or atrium. The signal then travels to both the right and left atria, causing them to contract and push blood into the lower chambers, or ventricles. The electrical signal continues into the ventricles via the atrioventricular node, or AV node, and then into the tissue that separates the ventricles called the bundle of His. The signal continues down the bundle and into the left and right bundle branches, located within the ventricles. When the signal reaches bundle branches, it causes the ventricles to contract and pump blood to the lungs and body, completing the heartbeat. The conduction system functions as the body's own pacemaker and keeps the heart beating at a normal rate of 60 to 100 beats per minute. If the activity of this system is interrupted due to heart damage or other medical conditions, it can cause the heart to beat at an abnormal rate or with an irregular rhythm. Should this occur, blood flow to the brain and other parts of the body could be compromised.
Okay, so I think that these are all good little video clips that help us understand how this conduction system works. So hopefully you've already written these notes down. If you haven't, you can pause the video and get them down. The video as well as my conversation is what explains that, okay? I want you to see, it is kind of hard to see what's happening here. My cursor right now is on the aorta. It's coming out of the left ventricle going into the aorta, which means this is the left side of the heart. Okay, this being the right side of the heart, the top portion is the atria, and they treated this heart with some specialized chemicals in order to allow us to see the neurons that are there. So this silvery substance that's here in the atria, that is going to be the specialized myocardial cells that are going to stimulate the heartbeat. Okay, we can see some here. We can see some in the interventricular septum, okay? So again, specialized myocardial cells are going to cause the conduction system of the heart to work, and that conduction system is explained here in these 5 steps, okay? So you don't need to write this part down because you've hopefully written it down this way, all right? Anyway, so in your lifetime, you are going to have a heartbeat, and here is the age relation of your heart rate to age. And you'll notice that before you're born, you have the greatest heart rate. The heart rate can be as fast as about 160 beats per minute. And then slowly as the fetus develops inside the mother, the heart rate drops. And when a baby is born, their heart rate is usually somewhere between 100 and 160. So you can see the cross line on my chart here is going to be the average, but then this is the range. And then you'll notice after a child is born, it just continues to fall until we reach somewhere between 60 and 80, okay? You'll notice right here that this right here brings the heart rate all the way down to 40. And if you think about what happens in our 20s, in your 20s, you're your most physically fit. This is when college sports take place. This is when people are young and healthy. And sure enough, the lower your heart rate, the more fit you are considered to be. Also, how quickly your heart returns to the normal resting heart rate is another indication of your overall fitness. And then you can see the age groups go up, go up, go up. Okay, so I'm right here in this 50 to 55, and sure enough, my heartbeat should be somewhere between 50 and, well, let's just go between 60 and 80. And sure enough, my resting heart rate usually is right around 60, 66. So that's the age to heart rate chart. Your heartbeat is going to be affected by how old you are. We just covered that. Whether you're a male or a female, the heart rate is generally greater in females because females are smaller. So when we think about the average height of a male, I want to say the average height of a male in the United States, the last time I checked, which was a long time ago, was 5'8". And the average height of the female was 5'6". Well, I am a female, but I'm 5'10". So would I fall into the heart rate of the smaller female or the larger male? All right. So it's just a generalization. The only reason why the heart rate is greater in females is because in general, females are smaller. If you compare large females with small males, well, your comparison then would show different results. Your heart rate will also increase based on the position of your body. If you lie down and just relax for a few minutes, you can get your heart rate to probably go to its lowest. Because you're flat, your body is no longer fighting gravity, and your body has a chance to relax, and your blood flows the most easily that way. Physical activity, again, if you're out walking, your heart rate's going to increase. If you're running, your heart rate's going to increase. If you're scared, so thought process is listed there as well, your heart rate is going to increase. Temperature is something that's interesting because your heart will accommodate for the temperature outside. If it is really hot and you're having trouble displacing heat from your body, your heart rate will increase to try to get rid of the heat. So your heart rate is very variable. It will meet the needs of your body as you go through your day. Okay, so if you have any questions, make sure to stop the video, pause, ask me in the chat. All right, super important. All right. The lub-dub sound of the heart. When we put our head on somebody's chest, we hear that lub-dub sound. And this is why. One interesting thing about this video is if you watch the right side here, this will show you the EKG. It'll show you the stimulation in the heart as it's working. Okay, so take a look at that. 24 seconds, not too long. Okay, so if you want to watch that again, it is linked on the notes. But the opening and closing of the valves is why we get heart sounds. Okay, so this right here is an EKG. An EKG is amplified current shown on a screen. Okay, so if you guys take a look, you will see that your heartbeat is shown on this screen here. This is a normal EKG. And then doctors can tell when something's wrong because then it doesn't look the same. And this next one is the one that we really worry about. Actually, I don't know if ventricular fibrillation is on here. No, just atrial fibrillation. So atrial fibrillation is something that is telling us that the atria is not working correctly, okay? But ventricular fibrillation is something that, sure enough, is deadly, okay? So make sure that you have this written in your notes. And then here is a diagram that shows which part of the wave is represented by what's going on in the heart. So as the action potential comes out of the sinoatrial node, that is that first rise in the EKG, all right? As it spreads out across the atria, you're then going to see it here. And as it gets to that pausing point where we now have the blood moving from the atria into the ventricles, we then will see this little gap in time here, if you can see my cursor, okay? Then we have a big amount of electricity that's going to move through and down the heart. So this is moving through and down the heart. And as the heart squeezes, we get this big up at the very end of the heart contraction. Okay, so the EKG is known for its P, Q, R, and S and T waves. The P was the atria depolarizing. Yes, you need to have this in your notes. The QRS is the ventricles depolarizing. And then at the end, we see the repolarization of the ventricles. Now, the atria needs to repolarize as well, but that signal gets lost in the loud signal of the depolarization of the ventricles. So we do not see that on an EKG. All right. The last thing that I would like you guys to be aware of is that we have pressure in our arteries. If you didn't have pressure in your arteries, the blood would not flow, okay? So when your heart squeezes, well, we call that your systolic pressure. When the heart is squeezing, there's extra pressure on your arteries. And that, again, is going to be the top number in your blood pressure, okay? Then when your heart relaxes, when the blood's moving between ventricles and the atria and out into the aorta, we have our diastolic pressure. And that is when the arteries are not under the force of the blood being pumped into it. And that is the bottom number of your blood pressure, okay? So we are going to talk more about blood pressure. We are going to talk more about EKGs, but I hope at this point you understand all of these concepts. Please make sure that if you have any questions, you pause your video and ask them, or you put them in the chat. Make sure to access all that information. All right, thank you for watching the basic physiology of the heart.